Well, I hope this is working. That's the recording part. Today we're going to do chapter 12. This isn't the perfect venue for slides in this room, but nonetheless, we are here. Today we're going to start off by talking about valence and the concept of orbital hybridization. Simple and branched alkanes. We're going to learn how to draw simple organic compounds, nomenclature, isomers, functional groups, amino acids. Then we'll talk a little bit about proteins, DNA, fats, and metabolism. Just as a reminder, on Monday, there is no class, number one. Number two, quiz 2 will come online. Do it. You must complete it before the second hour exam. Wednesday, there's no class because we're all busy cooking. Right? Right. So, now, fast forward to the next week. On Monday, we will meet back in the H building, and we will do sample exam number 2. As always, print yourself 2 copies, work 1, hand it in, get 10 points extra credit. Don't forget to do that. It's a simple thing. The following Wednesday, we get to be back here, and we will take exam number 2. Also, don't forget the assessment. The department has sprung this on me and you. This covers chapters 1 through 9 essentially. Worth 16 points of extra credit to you. Again, you have to do it before exam 2. Any questions before we get started? All right, well, let's just talk about a very simple concept of valence. Valence is the number of bonds an atom forms in its neutral ground state. For oxygen, look at water, is 2. 2 unshared pairs of electrons. Nitrogen is 3. 1 unshared pair. Boron is also 3, but has no extra electrons. Poor boron. It's stuck in life with only 6 valence electrons around it. But carbon has 4 bonds always. Neutral carbon. There are 3 varieties of neutral carbon that we will deal with. This where the carbon has 4 single bonds. This has a carbon-carbon double bond, and this is a carbon-carbon triple bond. When we're counting valence, each of these bonds counts as 1, so 1, 2, 3, 4. Everybody has 4. Now, carbon is in the second period. We don't have a periodic table we can see, but atomic number is 6. For the electron configuration, well, we're right here. We would expect the first energy level to be filled. That's the 1s2. The next 2 electrons would go in the 2s. So we have 2s2. And we have 2 electrons left over. So 2p1, 2p2. Something like that. Putting it all together, looks like that, or 1s2, 2s2, 2p2. Now, think about that for a second and the fact that carbon always has 4 bonds, valence of 4. These are the electrons that we're working with. You know, as I look at this, I would expect, maybe pairing up electron here and here, and have a valence of 2-ish. But we don't. Quite clearly, it's a 4. The reason it's a 4 is that energetically, instead of doing just 2 bonds, energetically it is more efficient for the carbon atom to take one of the s electrons, promote it to a p orbital. So we wind up with a hybridized set of orbitals. These are 1s and 3 p's all combined. Mathematically, what you do is you calculate the geometry that gives you the least interaction and the lowest overall energy. This is sp3 hybridization. Remember that. So a carbon with 4 single bonds looks something like this. The geometry is tetrahedral. All of the bond angles are 109.5 degrees. Now, in kindergarten, they teach you shapes, but they never teach you the important one for some reason. This is a tetrahedron. The carbon here in the middle is equidistant from each of the corners. And again, all of these bond angles are the same, 109.5 degrees. Now, every carbon compound that has this array of single bonds will basically look like this. Instead of having hydrogens attached, however, carbon compounds can attach to more carbon atoms and other atoms as well. An example, here we have 3 carbons in a row attached to each other, and they all have 4 bonds around them, 3 hydrogens, 2 hydrogens, 3 hydrogens. Now, all of the bond angles here are also 109 degrees. Typically, if you were to draw this thing out, you would use something that might reflect that geometry. The real geometry looks like this, and we'll see that this zigzag mode will carry on when we draw simple carbon compounds as well. In place of one of these hydrogens, we could easily stick in another carbon. This is called a branched chain alkane. Now, what's an alkane? Well, an alkane is a functional group. Functional groups in organic chemistry are groups of compounds that share structure and reactivity. There are so many compounds in organic chemistry, so many reactions. The advantage of grouping things by functional group is that if they contain that particular functional group, it really doesn't matter what else is attached. They're all going to react the same. So we'll see that in just a few minutes. Again, this is a zigzag molecule. This is what it would look like as a model. Here's our CH3 sticking off. We'll call this the main chain. And therefore, this is a branched main chain. If you have an alkane, that's the functional group, it will have a general formula of CnH2n plus 2, where N is simply the number of carbon atoms. Here we have 3 carbon atoms, so N is 3. That means we should have 8 hydrogens, which we do. Here we have 1, 2, 3, 4, 5 carbons, N is 5. We have 12 hydrogens all around the compound. Now, like I said, there are 2 other functional groups that we will talk about a little bit later. They involve carbon-carbon double bonds. Anything with a double bond we call an alkene. This is ethene. We'll talk about the nomenclature. Anything with a triple bond, the functional group is an alkyne. Again, this is ethyne. Anything with a carbon-carbon double bond will undergo a set of classic reactions defined by an alkene. Makes doing organic so much easier. Now the word F. F stands for 2 in organic language. Meth is 1, eth is 2, prop, bute, pent, hex, hept, oct, and way up there. You probably should know like up to oct, that's 8. Not too different from nomenclature that we've done before. Again, the formula is always CN H2N plus 2. When you have a chain, a parent chain of some sort, and you have a branch coming off of it, that branch that comes off is referred to in general as an alkyl group. Alkyl group, often called R for just a radical, an alkane radical. You take the alkyl name and replace the A and E with YL. So if we're dealing with 1 carbon, that's a meth. So this is methane. Take a hydrogen off, attach it to somebody else, and we have a methyl group. If we had 2 carbons, it would be an ethyl group, whatever. If we attach this 1 carbon unit to an OH group, that would be an alcohol, that's the new functional group, and would be called methyl for this, alcohol for the OH. Same thing for an amino group, methylamine. Just the way the nomenclature works. One more time, 1 carbon is a meth, 2 is an eth, 3 prop, 4 bute, 5 pent. Now the really neat thing about carbon compounds is that you can have such amazingly diverse structures. These are just some simple things. Here's just a simple alkane with a branch. Here are 6 carbons attached in a ring. This is a polycyclic ring, so we have 1, 2, 3 separate rings all fused together. One of the great challenges in organic chemistry, if you're given a compound, is trying to figure out what the heck the structure is. Very, very analytical discipline. We can also replace these carbons with other things. This is glucose, this is morphine. Nitrogen is blue, oxygen is red. When we have other things in an organic compound, we refer to them generally as heteroatoms. Organic chemistry is very carbon-centric. Okay, it developed first. And organic chemists tend to think of carbon as it and everything else as something other. So that's just the discipline. Representing them, these are models. We've done ball and stick, we know what that looks like. A guy named Dryden did a ball and stick model one day and left the balls off and got his name put on the model. It's a nice compact little thing. It's basically just a ball and stick with no balls. This is space filling. Again, all 3 of these are on the same scale. So this is what this molecule really looks like in 3D space. These are much easier to understand what's bonded to whom. When we're going to represent a carbon compound, The simplest and most useless way is to just give the molecular formula. This has 4 carbons, C4, 10 hydrogens, C4H10. Tells you nothing. Quite often you will see what's called a condensed structure. Condensed structure tends to try to follow along the main chain of your carbon compound. CH3 bonded to a CH2, another CH2, and another CH3. It does a fairly decent job of showing you what's bonded to whom, but doesn't tell you much about the geometry. The ultimate description is called a Kekulé drawing. Kekulé drawing, you show all the hydrogens, all the bonds. They're a real pain in the whatever. You don't ever do those. What people do instead is a shorthand version called a line drawing. Line drawing has a couple simple rules. Every spot here represents a carbon. So this is 1, 2, 3, 4 carbons. A truncated line, that means it goes up and stops, represents a methyl group, a CH3. A vertex, so where there's 2 lines joined together, is a CH2. So you look at this and you say CH3, CH2, CH2, CH3. Same thing we have here. Also, remembering that we have a zigzag backbone. These are quite often done like this, again to represent the geometry. Now, as pure and simple as this is, you will also see it represented lots of different ways, because people worry that students will look at this and won't realize that this is a methyl group, and so is this. So quite often they will just put them in, CH3 and a CH3. All right, makes it easier to remember, right? Purists, however, look at this and say, gee, this looks like this carbon right here is bonded to these hydrogens. That's not right. So you take this and you flip it around. This is much more accurate. Again, writing things backwards is a bother. Any questions? Now we will use line drawings in some combination of these as we do structures. Typically, we're going to use rather pure line drawings. There are 2 other versions of line drawings that are useful. Start off with our line drawing here. In organic chemistry, it makes a real difference. The orientation of things relative to other things. That is the stereochemistry of the molecule. In order to show that, using more or less a line drawing, people have developed what's called a sawhorse projection. In the sawhorse projection, you're just taking this and turning it on an angle. So this is now the front carbon, this is now the back carbon. All you've done is rotate it so you can see it. Again, this is important because this tells you very clearly that this methyl group is on the opposite side of this methyl group. And in organic, that matters. There's one structural version that should go a bit further. If you take this and rotate it all the way, so this is in front of this one, you get what's called a Newman projection. The same three things here. This is our front atom right here. Oops. This is our front atom right there. The back atom we make big so that we can see what's attached to it. So let's just look at a little video that shows how this happens. This is our Dryden model. Going to rotate it. This is now the sawhorse. Rotate it all the way. This is the back atom. This guy is the front. So let's look at some structures and see if we can unwind them and make them into line drawings. When you do line drawings, one thing to remember, artwork counts. If you have a structure that you're drawing for me and it's absolutely beautiful, I am much more likely to look at it and say, yep, that's good. But if you make the correct structure and it looks like a scribble, no. Artwork is important. So, let's look at this condensed formula and see if we can unwind it. The rule in the condensed formula is that if we have things that are attached to one of the carbons, we show those in parentheses after the carbon. So, this is one carbon, two carbons, 3, 4, 5 carbons in our chain. This little thing here tells us that on carbon 2, we have 2 methyl groups attached. So, first thing you want to do, and you can do this in real time, write a zigzag with 5 carbons. It's an important thing to do to make sure you know when to start and stop your zigs and your zags. Well, we're going to start here with 1. Go up, go down, go up, go down, and we're done. Something like that. 1 carbon, 2, 3, 4, 5. Now, on carbon number 2, that's this guy, we're going to have 2 methyl groups. Again, we show those as lines going off into space. There's 1, there's 2. This is this molecule as a line drawing. On exam number 2, one of my standard and or favorite extra credit questions is to give you something, and ask you to draw it as a line drawing. So make sure you have this skill. This guy, this has 1, 2, 3, 4, 5, 6 carbons in a ring. Remember, the geometry of carbon is such that the zigzag is carried over even if you have a ring structure. So, if you're going to draw this as a line structure, just start somewhere. You want to go up, down, up, and down, completing the ring. Now, just to show that organic chemists have somewhat of a sense of humor, this is referred to, well, this is cyclohexane. This is referred to as chair cyclohexane. Because if you really imagine, you could think this kind of looks like a lawn chair. Yeah. There's also a boat that looks different, but if you want, instead of drawing the chair, it would be perfectly acceptable to draw a perfect hexagon. The key words there are perfect. The last guy here, well, this is a Newman projection. We're going to have to untangle this and figure out what our longest chain is and who's attached to it. So let's start somewhere and number. 1, 2, that's the front carbon, back carbon, 5, and 6. So if we go down, back, and out, we have 6 carbons to work with. That means we need to start this with a 6 carbon zigzag. Now I put 3s and 4s here because if you look at this, trace it out, on carbon 3 we have a methyl group, don't we? On carbon 4, which is the back carbon, it's another methyl group. So we have to show those in our structure. We do that just like here. We're going to put in truncated lines. Methyl group number 1, methyl group number 2. Any questions? All right. We draw these structures and we're really proud of our artwork. And yes, they look nice and blah, blah, blah. You must remember, however, that in reality they look nothing at all like this. And that's because every time you have a carbon-carbon single bond, the groups attached around that single bond are going to rotate like this. Go around and around and around about 1,000,000 times a second. So if we had this as our structure, these bonds are just spinning around like mad. So instead of drawing it this way, if we drew it this way, it would be the same thing, wouldn't it? We have 1, 2, 3, 4, 5 carbons in a chain, a 2 carbon side chain. We have 1, 2, 3, 4, 5 carbons in a chain and a 2 carbon side chain. These are just spinning like mad. They're referred to as conformational isomers. And because they spin so quickly, this and this are considered to be the same molecule. We can't separate them. They're the same. This is just a little quick video that's not great, but kind of shows, slowed down 1,000,000 times, what a simple alkane backbone really looks like. So here we go. It's going to do its dance for you. Everything is spinning, everything is wiggling. Again, all these conformations define the same molecule. Slowing this down and or extracting them. This is an alkane with 1, 2, 3, 4, 5 in a methyl group. So is this 1, 2, 3, 4, 5 in a methyl group. 1, 2, 3, 4, 5 in a methyl group. Again, they're all the same. Any questions? All right. Let's figure out how to name simple alkanes. Now, like I said earlier, organic chemistry is a very, very old science. And back in the old days, so we're talking mid-1800s, if you discovered a molecule, you could name it anything you wanted to. So, here's George. The problem with that is that there are so many organic compounds that you need something systematic. The International Union of Pure and Applied Chemistry, IUPAC, stepped in and said, these are the rules we will follow. Rule number 1, look at your thing and find the longest continuous chain of carbons. So, look at this guy. We could do 1, 2, 3, 4, 5 carbons, right? Or we could do 1, 2, 3, 4, 5, 6. 6 is bigger. Our longest chain looks like this. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. 7 is bigger than 6. So, step 1, look at your thing, find the longest chain. Step 2, we're going to number the atoms in the longest chain, beginning at the end that's closest to the first substituent. Substituent is a branch, or it's a halogen or an oxygen, something that's attached to this main chain. So we look at this. We have 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. It's going to be a 7 chain, 7 carbon main chain. Let's just use this one. That means that this end is closest to the first substituent. So we will make this carbon number 1. 1, 2, 3, 4, 5, 6, 7. Again, this would be carbon number 1. Okay, that's carbon 1. That must be 2, 3, and 4. Next, we're going to name the substituents attached to our chain. We're going to call them alkyl groups. And the alkyl group name is going to be based on the number of carbons. Okay? We're going to take all this, arrange them alphabetically as a single word using dashes and commas, and come up with a name. So, we look at this. First thing we say is here at carbon 2, we have a methyl group. Keep that in your head. Over here at carbon number 4, we have 1, 2, 3 carbons attached. 3 is prop. So this is a propyl group on carbon 4. We look over here at our last carbon. This is 7. How do we say 7 in organic? It's a hept, H-E-P-T. It's a heptane. Now, we want to string these together alphabetically. Methyl comes first. It's in carbon 2, so we will write 2-methyl. Okay? Propyl comes next. We will write 4-propyl. Again, separating them by another dash. And finally, the parent here is a heptane. No dash, just heptane. 2-methyl-4-propyl heptane. Be much more fun to call it George, but any questions? Well, let's do another one. In this one, we're going to have multiple groups attached. So first thing, let's figure out our longest chain. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8. I think 8 wins. If this is carbon 1, it would be closest to the first substituents, wouldn't it? So we're going to define this as our parent. Now, the first thing we note is if this is our parent, we're going to have 3 total methyl groups. 2 of them here and 1 here. That's going to be a trimethyl. But we have to use numbers to show where they are. 2 methyls on carbon 2, a third methyl on carbon 6. We will write in our name 2, 2, 6 trimethyl. Gives the location for each of the methyls. Here in the middle, we have an ethyl group. That's 2 carbons, and it's on carbon 4. Now, alphabetically, we have 8 carbons, so it's an octane. Octane will come last. Alphabetically, we don't do tris or twos and stuff like that, but ethyl comes before methyl, so that has to go first. First thing we write down then is 4-ethyl. Put a dash. Then we need our 3 methyls. They're on carbons 2, 2, and 6. 2, 2, 6, trimethyl. Dash in front, dash afterwards, commas in the middle. Finally, it's an octane, and we stick octane in. Any questions? Let's do another. Here we're going to take the molecule we just had, but instead of our third methyl, I'm just going to stick a chlorine on. When you have a halogen attached, it would be chloro, bromo, fluoro, iodo, whatever. So this is a chloro group. So one more time, here's our main chain. That's still carbon 1. We have 2 methyls now on carbon 2. On carbon 4, we still have our ethyl group. And on carbon 6 here, we have a chloride, a chloro group. Again, it's 8 long, so it's an octane. Now, putting it all together, chlorine is going to come first alphabetically, so we're going to start off with 6 chloro. Let's see, ethyl comes next alphabetically, so that's a 4-ethyl. Methyl comes next. We have 2 methyls on carbon 2. That's a 2,2-dimethyl. And finally, it's still an octane. Now, on exam 2, it is not beyond the realm of possibility that you would be asked to name something. It won't be this. It won't be complicated like that. But it might look a lot like one of these. So very quickly look at these. Decide the longest chain. Decide who is carbon 1. And come up with a name. I'll pause for just a second. This is a sawhorse projection. If we look for our longest chain, going to be something like 1, 2, 3, 4, 5 carbons. Now we have a methyl group sticking out there. If this was carbon 1, it would be attached to carbon 1, 2, 3. If we let this be carbon 1, it would be attached to 1, 2, 3. So it doesn't matter which one we call carbon 1. All right. 1, 2, 3, 4, 5. That's a pentane, isn't it? What's attached to our pentane? In carbon 3, we have a methyl group. That's it. The name, 3-methyl pentane. The next guy, we have 1, 2, 3, 4. 1, 2, 3, 4, 1, 2, 3, 4. So it doesn't matter which chain you pick. Let's just pick one. This, if that was carbon 1, this would be 2 with 2 methyl groups. So that's good. We'll let this guy be carbon 1. It has 1, 2, 3, 4 carbons. That's a butane. What's attached to our butane? In carbon 2, we have 2 methyl groups. Going to be 2, 2 dimethyl butane. These would be entirely eligible for test questions on exam number 2. So make sure you get this. Sometimes I also do it backwards. Here are names, draw a structure. Beautiful artwork. We have a butane, that's 4 carbons. Draw our zigzag. Pick one end to be carbon 1, doesn't matter which. We're going to have 3 methyl groups attached. 2 of these will be attached to carbon 2 and 1 to carbon 3. 2 on carbon 2, 1 on carbon 3. Our next guy, 3-ethyl-2,2-dimethyl hexane. Hex is 6, right? So we're going to put our zigzag with 6 carbons. 1, 2, 3, 4, 5, 6. Now in this, on carbon number 3, that's here, we're going to have an ethyl group, that's 2 carbons. On carbon number 2 here, we will have 2 methyls. These are simply lines. This is a line going up and over, and it would look like that. This last one actually was an extra credit question. So look at it and think about it. It's an octane. Octane means 8 carbons in a row. Step 1, draw your zigzag. To find something as 1, we have 1, 2, 3, 4, 5, 6, 7, 8. Yep, that's an octane. Now we're going to have 6 methyl groups on this compound. And they will be at carbons 2, 3, 4, 5, 6, and 7. Carbon 2, 3, 4, 5, 6, and 7. And they would look like this. Two, three, four, five, six, 7 hexamethyl octane. Any questions? Again, on the exam, it will be comparable to this, or maybe the slide we had before, or it'll be something totally different. But you will have questions from Chapter 12. Make sure you get this. All right, let's go a little bit further into the notion of double and triple bonds. How do you make these guys? This is called a hybrid that's sp squared. That means you take one s and two p's and you make this, the double bond. This is called an sp hybrid. So let's do this one first. This is one s and two p orbitals. We have 3 orbitals, we can make 3 bonds on each carbon. When we have 3 things attached, the geometry is going to be simple and planar. 120-degree angles. So that's your skeleton. However, we've only used 2 out of our 3p orbitals, haven't we? We still have 1 left for each carbon. If we take the leftover orbital and show it here and here, that's what you wind up with. Now, these are aligned perfectly. And by being aligned, that means that these electrons can interact with both carbons on the top and on the bottom. We wind up with this. This is called a pi cloud because it's made from p bonds. If we cut this open and look, well, it's kind of like a hot dog bun, but here's the hot dog inside. This is the first bond, if you will, in our double bond, and this pi cloud represents the second bond. We draw it like this. Again, 1 bond for this guy. We show this one as another bond, but we realize that it's really a pi cloud. If we do electrostatic potential map of it, see the big red splotch? That's that guy. In a carbon-carbon double bond, this is where the extra electrons live, and that defines the reactivity. It also does something else interesting. In order for these guys to line up or to interact, they have to line up nicely. If we take and we twist this single bond here in the middle, so it looks like that, they would no longer interact. That means there's a big energy barrier to this rotation. That also means if you have a carbon-carbon double bond, you can have at least 2 isomers. Here, trans, where things are on opposite sides, and cis, higher energy, where they're on the same side. This particular bit of geometry is extremely important in biochemistry and physiology because vision comes down to a simple chemical reaction. This is retinal in a cis configuration. This is the higher energy form. Let's pretend that this is sitting at the back of your retina, bound to a protein, and by George, a photon comes in and hits it. When it does, this goes to an excited state, and in the excited state, you can go to the lower energy form, the all-trans retinal. Now, as you note, the shape of the molecule changes, doesn't it? The protein that it's bound to senses the fact that it's changed, sends a signal to the brain that says, I just saw a photon. That's vision. Simple cis-trans isomerization. Things that differ in space in organic chemistry, we call these stereoisomers. Quickly, let's do the SP. One S and one P, two bonds. Got to be linear. Again, we have two p orbitals left over for each of these atoms. If we put this and this on this one and this one, you wind up with that. Once again, this is going to form two sets of pi bonds. So two hot dog buns, one on the side, one on the top. This is the first bond of our triple bond, the second bond, and the third. If you look at the electrostatic potential map, big belt of electrons around the middle. So, important things to remember here. We have single bonds as sp3 hybridization. We have a double bond as sp squared. A triple bond is simply sp. These are the functional groups: alkane, alkene, and alkyne. Now, once again, a functional group. Everything with a double bond is going to share reactivity. It's going to be the same. This is an alcohol. It's an OH. All alcohols have similar reactivity. Put the oxygen in the middle, we get an ether, another functional group. All ethers have similar reactivity. Now, when I say reactivity, this is what I mean. If we just take a generic alkene, doesn't matter what's attached, react it with bromine, we wind up with a 1,2 dibromide, and the bromines are always on opposite sides of the molecule. One of the things you do in organic chemistry when you see something like this is try to figure out why. Well, this pretty much explains it. If we look at cyclopentene, here's our double bond. This is bromine. Remember, there's a big electron density right here. This is going to reach out and attack Br2. We show this with arrows in organic. We wind up with what's called a bromonium ion, basically Br plus, sitting on top of this little pile of electrons. We lose this as Br minus. Now, the one thing about a bromonium ion is that it's big. We have this Br minus that would love to react with this, but because this is so big, it's taken up the whole top. The only way that Br minus can attack is by sneaking in the backside. That means we wind up with bromines on opposite faces. Now, when I say that alkenes all share the same reactivity, they do. For my organic classes, I made sets like this. These are all reactions of a generic alkene giving products. Organic is not trivial. There were 3 of these sheets in the set. Got to remember them all. All right, let's just quickly run through the rest of the functional groups. We've done alkane, alkene, alkyne. We take 6 carbons, put it in a ring with double bonds. Each of these guys has a p orbital left over, right? So it really looks something like this. They're all sticking up the same way above and below, so they overlap, and you wind up with this beautiful collection of electrons in the middle. Again, that defines the reactivity. This is benzene. Beautiful molecule. Carcinogenic, but if we have a halogen attached, it's called a halide. An alcohol, oxygen in the middle is an ether. Remember this guy. If we put a nitrogen on it, it's called an amine. Put cyanide on it, it's called a nitrile. And put a nitro group, an SH makes it a thiol. The one thing you remember about thiols is that they stink badly. The essence of skunk are thiols. Sulfides stink too. I wouldn't mess with those either. If we have a carbon that's doubly bonded to an oxygen, it's called a carbonyl. Very important functional group. We name them depending upon what's attached to one side. It's carbon on the other. If we have a hydrogen, it's an aldehyde. Another carbon's a ketone. Remember this guy. This is called a carboxylic acid with an OH attached. An ester, instead of hydrogen, we put another carbon. An amide, instead of the hydrogen or whatever, we put a nitrogen. Remember him. Put a halogen, put another carboxylic acid, we make an anhydride. Carbonyl chemistry is really central to organic and biochemistry simply because this group is so polar. This is acetone, nail polish remover. This dissolves things very effectively because the molecule in the electrostatic potential map is extremely polar. Positive end, negative end. Remember how the electrons in an alkene reached out and attacked the bromine? Well, this is a huge positive spot. Things with electrons come and attack that carbon. Now, when we were talking about functional groups, I said you should remember amine, carboxylic acid, amide, whatever. That's because in biochemistry, we have amino acids. All amino acids have the same basic structure, starting with this carbon in the middle. We attach an amino group to it. We attach a carboxylic acid to it. And we will have this thing also attached, which is called the side chain. Amino acids basically differ in what's in the side chain. This and this and this are all positively charged. These guys are negatively charged. Here's a set that are polar, so they're water soluble, but they're not charged. These are special cases. We have a thiol. You can put a selenium in there instead. Just a hydrogen, proline, kind of wraps around itself. This is the amino acid that predominates in hair. Why hair can get curly. We also have the other set here, hydrophobics, methyl group. Here we have a branch chain, another branch chain, another branch chain. A sulfide, even have benzene rings in our amino acids. Now, the thing that amino acids do in your body is they will link to each other. This is going to involve the amino group of 1 attacking this carbonyl. When we do that, we're going to lose water. And we make a bond. This is an amide. Now, this little short thing, 2 amino acids, is a peptide, it's called. It still has a carboxylic acid and an amino group, so we could do this again on either end. Make another amide, make another amide. Here we have a peptide with leucine, glycine, serine, and alanine. We could do this all day. And if you do this all day, you wind up with a protein. Long chain, all bonded by amide linkages. Now is when side chains are important, because this long chain is going to wad itself up into a ball. When it does, all the things that are water soluble will be on the outside. All the things that are water insoluble will be on the inside. This is a ball. This is the protein, amino, or enzyme, lysozyme. You'll see that as these things go together, this is called a helix. They form alpha helix. This is a beta sheet. This is hydrogen bonding between the various amino acids. The thing that's amazing is that every molecule of lysozyme looks exactly like this. You can also show the coils using a ribbon. Makes it a little cleaner. If you do a simple space filling model, yeah, but you can't really tell what's going on in there, can you? But you can see one thing. See this thing right here? That's his mouth. It's a crevice in the side. It's lined with charged groups. What happens is that starch, polysaccharides, sugars all hooked together come up and they bind in this little spot, in this little crevice. When they do, the charged groups on the side catalyze the cleavage, and you've broken your starch chain down. That's how an enzyme works. DNA and RNA. The difference is, this is a ribose right here. For DNA, instead of having the OH where it's supposed to be, there's just a hydrogen. Deoxyribonucleic acid. In the body, these guys are bound to what we call bases. These are purines. They have 2 rings. We also have pyrimidines. Look like this. In RNA, thymine is actually substituted for a slightly different structure, uracil. These are the bases for nucleic acid. And what's neat about them is that they can interact with each other very specifically. Here we have a guanine and a cytosine lined up next to each other. Now remember hydrogen bonding? Here we have an NH and an oxygen. They can hydrogen bond. NH and a nitrogen, another hydrogen bond. NH and another oxygen, and a third. This hydrogen bonding allows guanine to recognize cytosine. This is how strands of DNA can line up. The outside of the strand is this polyphosphoric acid residue. That's the outside. And on the inside, you can see these are all neatly bound together. You can also see it nicely this way. Here's all the bases that are called hydrogen bonding to each other, with the phosphates all on the outside. If we do space filling model, again, these are all the phosphates. You can't really see the base pairing inside very well, but it's there. If we go down to ball and stick, you can see the base pairing better, and this is a nice view of the polyphosphates. So that's DNA and RNA. The last of the groups we're going to talk about are fats. This is the fatty acid. This is the carbon-carbon double bond. What's the geometry? Well, it's cis. You've probably heard of trans fat, right? Real fat in your body is cis, higher energy state. Trans fat, we have a trans double bond here. It's lower energy, but your body cannot metabolize it. Your body can only do cis. So if you have trans fat, it just goes to your hips and stays there forever. Put three of them together, we get a triglyceride. This is what we typically regard as a fat. Take two of them, attach it to a very polar end. This is phosphoric acid and an amino group. This is very water soluble. This is not. This is how we make membranes. All of the water insoluble stuff groups on one side. These form a barrier on the outside. This is a biological membrane, surrounds every cell. Now, this is fluid. It's designed to look fluid because it's a gift, but yes, it's fluid. In fact, if it was just made up of phospholipids, it would be too fluid. So your body fixes that with a unique molecule called cholesterol. Cholesterol, very hydrophobic, looks like a paddle of some sort. It embeds itself in this lipid bilayer. A typical membrane will have 30% cholesterol, and it stabilizes it. Now, cholesterol, extremely important molecule in your body. Every cell knows how to make it. Your liver makes every bit of cholesterol that you need. It spits out the rest. But cholesterol, for all it's good, has a terrible reputation. And that's because if you look at arterial plaques, this yellow, greasy, ugly stuff is about 80% cholesterol. But It's not just cholesterol. We'll see that in just a second. All right, here's the story. Back in the 50s, we had a president named Dwight Eisenhower. Looked like a nice guy, former general. He loved his steak and eggs for breakfast, whatever. Had a heart attack while in office. Now, in those days, they could not do open heart surgery. Oh my goodness, no. But they managed to take little bits of his arteries anyway and determined that they were, quote, clogged with fat, and that fat was mostly cholesterol. Well, that was bad. They put him on a diet. They said he could eat no fat and nothing containing cholesterol. Well, that really kind of irritated him, so he died anyway. Nonetheless, this simple event forced the country and most of the world into a low-fat diet craze. We were told, no fat, no cholesterol. So what do you eat? Carbohydrate. This was the new meal. Yep. Sit down and eat spaghetti, drink Coke. Everybody will be happy. Problem is, everybody was happy, but, well, this is what I used to look like. And then the diets changed, and so did everybody else. Low fat, high carbohydrate wasn't working. It still doesn't work. A one-slide version of all metabolism. When you eat something, the digestible parts are broken down into this molecule. The carbons from it are these two on the end. This is the carrier CoA. In order to do metabolism, you must convert your food into acetyl-CoA. Now, the problem here is the rates of this are very different. If you take carbohydrates, very quickly you make acetyl-CoA. If you take fats, it's slower. If you take protein, very, very slow. Alcohol wins, though. It goes very, very quickly. It is metabolized very quickly, but the carbons in alcohol very seldom, if any, if ever, wind up as acetyl-CoA. That's why alcohol is referred to as empty calories. It's metabolized, you get a little bit of energy, but you can't do anything with it. All right, so sugars are fast, fats are slow, proteins are the slowest. What happens if you eat these two meals? Chips and a Coke. Well, you eat your chips and you drink your Coke. What happens? The Coke is just sugar water. That's going to be converted to acetyl-CoA very quickly. Chips, potatoes, starch. As soon as it hits your stomach, goes to sugar, goes to acetyl-CoA. What's left over? 30% of this is fat. And that's metabolized after your body is done with the carbohydrate. If instead you enjoy your steak, the first thing that's metabolized here is the fat, because the protein is metabolized so slowly. You don't get fat, and it tastes great. Bottom line here, Fat doesn't make you fat. Fat plus carbohydrate makes you fat. About 2 months ago, there was a paper that appeared just talking about dietary cholesterol. Now, you can walk up to any dietitian these days and say, what animal protein should I eat? I can guarantee you they will tell you fish, chicken breast. Never ever eat red meat or eggs. Eggs are huge amount of cholesterol in them. So does red meat. Well, it turns out, what this paper pointed out, is that cholesterol isn't really the thing that winds up in arterial plaque. It's not. It's oxidized cholesterol. This double bond, an alkene reaction, can be oxidized to form an epoxide. All right, the epoxide is a very reactive functional group. If it gets in your bloodstream, hits something, boom, it can stick. That's what's in plaque. So, the thing you want to worry about if you're eating cholesterol isn't cholesterol, but it's the epoxide. So what foods have the highest level of cholesterol epoxide? Fish and chicken breast. Which foods have the lowest? Red meat and eggs. Now, you have to cook your meat really red, your eggs really loose, but yeah, fish and chicken breast are the highest in the toxic form of cholesterol. No dietitian in the world will tell you that. Any questions? All right, let's just look. Quiz 2 on Monday. No class Monday or Wednesday. The following Monday, sample E2. Exam 2 is in this room the Wednesday after that. Don't forget the assessment, 16 points of extra credit. Here's our list of tutorials. Here's the deal. You're shooting for 350 on your total. Any questions? All right, guys. It's the end of the semester. Last chapter, we could celebrate. Bye-bye.